In 333 BC, Alexander the Great marched with his army into the city of Gordium in Turkey. There, he stumbled upon an ancient wagon. The wagon had a tricky knot tied to its yoke, puzzling everyone who saw it. Legend whispered that whoever could unravel this knot would rule over all of Asia. Alexander, ambitious as ever, decided to give it a shot. But despite his best efforts, the knot refused to budge. Frustrated, he paused and thought. Then, like a bolt of lightning, an idea struck him. He realized it wasn't about untying the knot, but about breaking it. So, without hesitation, he drew his sword and sliced through it. This daring move would later symbolize his remarkable ability to tackle impossible challenges with a fresh perspective. And as history unfolded, Alexander went on to carve out an empire spanning vast lands across continents, fulfilling the prophecy of the Gordian knot. We've got some tough nuts to crack nowadays, like how to tackle climate change, what to do if we run out of water, and how to make sense of the wild world of physics. Yeah, that last one might not be on your mind as you're scrolling through your phone or sipping your morning coffee. But it's a big deal for physicists because understanding it could unlock the secrets of the universe. Here's the deal. Modern physics relies on two big ideas that don't quite see eye to eye. General relativity helps us grasp the giant stuff like planets, stars, and galaxies, while quantum mechanics dives into the tiny world of molecules and atoms. Both are super successful in their own right. They make predictions like nobody's business. But when you try to mash them together, things get dicey. For the past half-century, scientists have been sort of dodging the elephant in the room. But pesky questions keep popping up that show how quantum mechanics and general relativity just don't want to play nice. Take a black hole, for example. Inside, gravity crushes matter into a speck smaller than a grain of sand. And then there's the Big Bang, where the entire universe burst forth from something tinier than a pinhead. In both cases, you've got the mega-big and the ultra-tiny happening at once, and our current theories struggle to explain it. That's the big puzzle of modern physics, finding one theory that can explain it all. And for over a century, scientists have been on the hunt for this ultimate theory, the granddaddy of them all, the theory of everything. Imagine the theory of everything as the mighty sword that cuts through all those tangled knots. Right now, there are a few contenders for this grand theory, but we'll dive into those later. First, let's figure out how we ended up in this knotted mess, starting with the concept of force. Now, when we say force, we're talking about the four big players in nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. What binds the universe together? In this video, we delve into celestial phenomena, from the mesmerizing dance of stars to the swirls of galaxies. From the birth of stars to the cataclysmic collisions of galaxies, each discovery unveils a new chapter in our cosmic saga. So, don't forget to share your thoughts and questions in the comments below as we embark on this cosmic adventure together. As any self-taught scholar of gum-wrapper wisdom might tell you, Sir Isaac Newton was the brains behind discovering gravity. He wasn't just a gravity guru, though. He also cooked up the laws of motion and cooked up some calculus on the side. But let's rewind to 1665, when Newton's gravity game began. Picture this: Newton chilling in his garden fortress because, plague season. Instead of hitting up lectures at Cambridge University, he's pondering life's mysteries. Newton wasn't big on just taking theories at face value. Nope, he liked to get hands-on, even sticking a needle in his eye to test stuff out. So, when he saw that famous apple tumble from a tree, he didn't just shrug it off. He thought, hey, why'd that apple drop? Back then, folks didn't have a clue about gravity. Some thought angels flapping wings moved planets around. Yeah, seriously, but Newton had a light bulb moment. Gravity pulls things down. Mind-blowing, right? He didn't stop there, though. Newton's brainiac move was saying, hey, gravity isn't just for apples, it's for everything, even planets. He cracked the code on why planets do their celestial dance and why apples make a beeline for the ground. Newton didn't just explain gravity, He connected the dots between what happens up in the stars and what happens down here on Earth. It's like turning two puzzles into one big picture. And that's the kind of magic a theory of everything aims for, just on a cosmic scale. Unification drove the discovery of electromagnetism, another powerful force. Electricity and magnetism were ancient knowledge by the late 19th century. Magnets, like magnetite and lodestone, existed naturally, while electricity, seen in lightning and electric eels, surrounded us. Some early studies hinted at a link between electricity and magnetism, but they were seen as separate. Then came James Clerk Maxwell with his groundbreaking Maxwell's equations, revealing they were just different forms of one force: electromagnetism. Now, let's talk about the last two forces in our quest for a theory of everything: the weak and strong nuclear forces. The strong force was pinpointed in 1973, and the weak force predicted in the 60s was confirmed in 1983. But first, a peek at subatomic particles. Ancient Greeks thought everything was made of tiny, unbreakable bits called atoms. This idea was close to reality. In the 19th century, scientists showed that everyday stuff like oxygen and carbon were made of these atoms. But soon after, they found atoms were made of even tinier parts: protons, neutrons, and electrons. Fast forward to 1913, and we're introduced to the solar system model of the atom, a classic we all know. But as our tech gets fancier and we dive deeper into the atom, we discover even tinier pieces of the puzzle. In the 1930s, physicists stumble upon the muon, kind of like a beefed-up electron. Then in the 50s, they find evidence for the neutrino, a sneaky particle that breezes through stuff like it's not even there. But hold on to your hats, because in 1968, researchers drop a bombshell. Protons and neutrons aren't the end of the line. Nope, they're made up of even teensier bits called quarks. And these quarks, they're the real deal, like the building blocks of the universe. They're so tiny, we can't even measure their size with our best gear. But hey, we used to think atoms were the smallest, so who knows? Maybe there's a universe of tiny grannies whipping up matter from pancake batter at the heart of it all. In just a few decades, physicists have discovered tons of subatomic rock stars with names like lepton and tau. Sounds like a lineup at a sci-fi convention. With all this subatomic chaos, physicists needed a roadmap. Enter the standard model of particle physics. It's like the holy grail of theories, giving us a solid grip on how particles dance in the subatomic realm. Did you catch all those mind-blowing discoveries about the tiniest building blocks of our universe? From leptons to taus, it's like a cosmic concert lineup. But hold on to your seats, because we've just scratched the surface. The standard model of particle physics is our roadmap through this subatomic jungle, guiding us through the mesmerizing dance of particles. If you're as fascinated as we are, stick around. There's a galaxy of knowledge waiting for you. Hit that subscribe button and join us on this journey of exploration. Together, we'll uncover the mysteries of space science one discovery at a time.